Anyway, we're talking about the mass defect and holding the protons together in the nucleus. When we make a chemical bond, you know, chemical bonds rely on nuclear forces or electrical forces. What holds together the atoms in a chemical bond? In fact, chemists are most interested in electrical forces. Do they care much about nuclear forces? No. Yeah, nuclear chemists do. And so, you know, what holds bromine chloride together as a chemical bond is covalent bond, which is electrical forces. You concentrate electron density in the bond region, and that attracts the two nuclei to the electron cloud in between the atoms. And so, do we have to worry about a mass defect in a chemical bond? There is no mass defect. I mean, we don't have to worry. In other words, well, I should take that back because you know, it turns out that even in chemical reactions, some of the mass, you know, an exothermic reaction releases energy, endothermic consumes energy. There are slight mass changes there, you know, but very, very small. So in general, chemists ignore the mass defect for these because it's negligible compared to how many digits. We have to read this like way down here to see any kind of mass change. Okay, because E equals mc squared does hold. But chemists will ignore it, or it's not significant. It's so not significant that we just say there's no mass defect. Technically, that's not correct. The reason we don't, you know, when we create a bond like this, we aren't cramming a whole bunch of protons into the nucleus, so we aren't changing the nucleus of the atom. And so the mass just adds up. And so we can get the mass of the molecule. Let's go ahead and get it. It's 71.9183 U plus 34.9689 U. So that's 12, 16, 17, 8, 18, 6, 106.8872. I must have made a mistake.
Yeah, it should be 78.
78? Thanks. 78. It's got to be closer to that. 1. So this is going to be 113. Right, 0.8872 U. So we don't have to weigh molecules in a mass spectrometer to get the mass. You can just add up the isotopic masses to get the mass of a molecule. Okay, so we have two choices. When we're looking at a mass of an atom, we only have pretty much one choice experimentally, and that's the mass spectrometer. Can we sum up the mass of the protons, neutrons, and electrons? Can we sum up those masses? No. Why? Mass defect. For the mass of a molecule, we have to be careful because we have to, you know, specify an atom of a specific isotope, you know, because each isotope weighs a different amount. For the mass of the molecule, you know, we could get the average, of course. The average would be a weighted average of all the masses for all the bromine chloride molecules. With the mass of the molecule, we could sum up the isotopic masses. That works. or we could sum up the average atomic masses off the periodic table. If we sum up the average atomic masses, we'll just get the average mass of a bromine chloride molecule. Or we could weigh it using mass spectrometer. Things we could do. All right. Tell me how a mole is defined. What is the definition of the mole? Somebody define the mole for me. Yeah, 1 mole is 6.02 times 10 to the 23rd. Where does 6.02 times 10 to the 23rd come from? That's Avogadro's number? How many sig figs do you know Avogadro's number to? 3. How many is it known to? A lot. Is it an exact number? Let me ask you, is Avogadro's number an exact number? It should be, but it's not. Why? Where does Avogadro's number come from? Somebody might ask you that. You don't, like I said. Yeah, the amount of atoms in 1 mole of. Well, how much is 1 mole? The amount of, I know how much 1 mole is, 6.02 times 10 to the 23rd. And so the amount of atoms in 1 mole of 6.02 times 10 to the 23rd. We call that circular, right? Circular because you're using 6.02 and you're calling it a mole. And so tell me how to get out of this circle. See, in Chem 4, it's okay. In Chem 4, 1 mole is 6.02 times 10 to the 23rd. It's Avogadro's number. It's 1 mole of anything. It's like a dozen, right? But as you go on, you know, it's not enough anymore. You need to know the definition, and the definition is, in fact, we need to know it now for this class. What is the definition of, in other words, where did that come from? I want to know exactly what it is. Okay, this is it. This is additional homework. Look it up. We'll talk about it Wednesday. Actually, no, I need to talk about it now. There's one more thing I want to talk about. Do you know how many grams are in a U, or U there are in a gram? How much does 1 U weigh in grams?
For the -6.
Or how much does a gram weigh in U? 1 U is 1 gram? No, it's off. It's off. And this is a conversion factor that you could look up in the book. You know, you could look it up in the book, 1.6, whatever. But everybody should know it. Everybody should be able to interconvert U to gram or gram to U easily. And it is very easy because what is the definition? the definition is this. The mole is defined as the number of carbon-12 atoms in exactly 12 grams of carbon-12. So if you had 12 grams of carbon-12, which is isotopically pure, because carbon in nature usually occurs as a mixture of carbon-12 and carbon-13. So you get rid of all the carbon-13 and you're left with just carbon-12, pure carbon-12 atoms. And so every single carbon atom is exactly the same. If you have 12 grams of that, then you figure out how many atoms there are. And so you could calculate it. And so based on that, or you could determine it experimentally, you know, the mole is approximately 6.0, we should know it to 4 sig figs, 6.022, a lot of sig figs, times 10 to the 23rd. This is like pi, you know, there's a bunch of numbers after that. It's not an exact number. But it should be because, you know, eventually you'll get to the very last atom. There's a huge number of atoms here. I guess you would know it to however many digits there are there. Why was the mole chosen as this? Why? Because it's related to the U. That's why. And so now there's a connection between the U and the mole. What is the connection between the U and the mole? U and the mole and the grams. And so what we have here is, you know, there are 12, actually let's go with this. There are 12 U in a carbon-12 atom, right? We know that this is true. 12 U per carbon-12 atom. And then we know that there are 6.022 times 10 to the 23rd U, no, sorry, that's wrong. 6.022 times 10 to the 23rd carbon-12 atoms is what we call a mole of carbon-12 atoms. And in 1 mole of carbon-12 atoms, there are exactly 12 grams of carbon-12. And so let's take a look at what happens here. The 12 cancels. The U does not cancel. The atoms cancel the atoms. Moles cancel the moles. And we get what? U per gram. And so there's 6.022 times 10 to the 23rd U per gram. And so the conversion factor is easy because it's the same as Avogadro's. There's an Avogadro's numbers worth of atomic mass units in each gram. And so U is a very small mass. If you invert this, then you get the number of grams in a U. The number of grams in a U is given in the back of the book. But anyway, looking at some of these problems here, a lot of these problems have to deal with natural abundance and dimensional analysis and this type of stuff. So we aren't going to go through more of these here. We're going to move on to the next chapter. Chapter 3, chemical compounds. Giving the definition of a compound. This is a compound. What's the difference between a compound and a mixture? Let's say a hydrogen-oxygen mixture versus a hydrogen-oxygen compound, like water. A hydrogen-oxygen compound like water versus a mixture of hydrogen and oxygen. Yeah, mixtures can be separated by physical means. That's good. Whereas a compound like hydrogen and oxygen, can it be separated by physical means? To separate the hydrogen from oxygen in water, you would need chemical means to separate it. To separate hydrogen and oxygen in a gas mixture is tough, but it can be done. Physical means. That's because the hydrogen and oxygen in the gas mixture are not bonded together, whereas hydrogen and oxygen in water are bonded together. And so hydrogen and oxygen compounds have fixed compositions, right? Mixtures have variable composition. So that's from chapter 1. So we're going to look at different kinds of compounds. Here's some crystals. This is sodium chloride crystals. We have different kinds of compounds. So let's look at the types of compounds we encounter. Yeah. What are the types? Usually the types of compounds are categorized by the type of bonds they have. Different kinds of bonds. And structure. Not just bonds, but also structure. Because what kinds of bonds do we have? We have ionic, covalent, metallic. Ionic, covalent, metallic bonds. Sometimes metallic, compounds are called mixtures because you can vary. For example, if you had a metallic mixture of copper and zinc, say, or no, maybe not copper, use something else. Iron and nickel. Since you can vary those, they don't have a fixed composition. We typically call those alloys. And so let's focus on covalent and ionic for right now. And so if we look at covalent, then what types of covalent compounds are there? There's molecular. Some of the elements form molecules. Do you know the ones that you should know? Some elements just in their natural state, like for example, chlorine forms diatomic Cl2. Do you know all those? Yeah. Yeah. So, yeah, some compounds like water, those are molecular. Water. What other types of compounds, covalent compounds, are there? Do some elements form single atoms, like neon? Neon is a single atom gas, right? Neon atoms, empty space. But how about silicon? Silicon form, what does that form? Molecules? Single atoms like mercury or neon? Silicon actually is a very high melting black solid, and silicon forms what we call network covalent structure. And so we could have network covalent. An example of this would be here. CO2? That should be molecular, carbon dioxide, right? Let's go down one. Rather than CO2, let's go to SiO2. You know what they call SiO2? Quartz. Quartz. Have you seen those, I'm sure you've seen quartz crystals? Quartz crystals? How close are quartz, silicon and carbon are in the same family. And so they should be similar in properties. How close in properties is carbon dioxide and quartz? Do you expect those to be in the same family? They are in the same family. Carbon and silicon are in the same family, but carbon dioxide and silicon dioxide are totally different because of the structure. You know, carbon dioxide forms individual molecules, whereas a network covalent solid, what happens with that is it forms what we call a lattice. In this case, it's a covalent lattice. This. And it just keeps going. It forms a nice crystal. And so it's a lattice of bonds. Neon forms single atoms. Well, what does carbon form? The element carbon. Is the element carbon, does that form molecules? Do we get carbon molecules? Actually, yes, we do get carbon molecules. Do you know what they're called? Buckyballs. These molecules that are 60 carbons in the sphere. And so carbon forms molecules, right? What else do we see? We see diamond. You know, diamond is made of carbon atoms too. Are diamonds? Those are allotropes. Good. We call these allotropes. Allotropes are the same element, different structure. And so one allotrope of carbon is diamond. Diamond, does it form molecules? Is it like buckyballs or water or something like that? No. Diamond is what we call network covalent lattice. This is a diamond-like lattice there. If we look at diamond, it looks very similar in a way, except oxygen only forms 2 bonds. But you know, diamond is going to have an extended network like this. It gives it certain properties. And so diamond's network covalent also. Then we have ionic. Do ionic compounds form molecules? You know, rare. You know, most of the stuff I say, okay, maybe there's one weird exception, but you know, ionic compounds, do we see molecules? For example, do you see molecules of sodium chloride when you look at these crystals? There's molecules of sodium chloride stuck in these crystals. Is that it? No. Ionic compounds don't form molecules, they form ionic lattices. And so if we were to look inside this crystal at the individual ions, what we'd see is we see an ionic lattice, you know, sodium chloride, sodium chloride, sodium chloride, sodium chloride, like this, and they're all just stuck together in a lattice. Here we have chloride ions, here we have sodium. Sodium ions are smaller than chloride. And so we get an extended 3-dimensional lattice like this, like we would for quartz or for diamond, except the bonds that hold them together are different. The bonds over there are ionic bonds, the bonds over here are covalent bonds. So we learn, in this chapter, we're going to learn about the nomenclature, and we want to know something about the properties of this thing. So what I'm going to do is I'm going to start off with this section, 3-4, talk about oxidation states. Oxidation states tell us a lot about the redox properties and other stuff about this. Have you heard of redox before? Redox properties? Redox? Redox stands for what? Redox. Reduction and oxidation. Do you know what reduction is? Yeah, gaining electrons. Oxidation is losing electrons. So they have oil rig. Have you heard of oil rig? Oil rig. Oil, O-I-L. Oxidation is loss or losing electrons. Reduction is gain. Gaining electrons. Oil rig. And so we're going to look at redox properties of these, and we're going to look at naming these things. And so as we do these formulas, we also want to calculate the oxidation state so that we can get some kind of idea of how these might behave. Because eventually, you know, like I said, you know, a lot of people will say, I don't want to memorize that, I'll just look it up, but you know, this can't keep looking up everything. So I was reading something earlier about, what was it? Actually, an article this morning, they were talking about research. You know, research versus a technician or something like that. You know, technician can always ask the supervisor what the answer is or what that is. But once you start doing research, and you start doing research early, I mean, you know, I started doing research at UCLA when I was an undergrad there, and the thing is, you don't have anybody to ask, you know, what the right answer is or this type of stuff, and so you know, how do you figure things out? Well, you have to do some memorization for sure to build up some basic knowledge, because you know, if you start looking up, I want to figure out the redox properties of this particular compound, but nobody's ever written anything about it. Nobody's ever said anything. You know, how are you going to figure it out? And so we're gonna start with this. How many people here have never done this oxidation state? Everybody should have done this, right? In Chem 4. Is that right? Everybody's done this? Nobody's not? Okay, good. Okay, what I'm going to do is I'm going to add a new twist to this. Okay, let's take a look at ethanol. There's certain ones you should memorize. For example, organics. Organics are important. And so let's talk about organic nomenclature right now. Organic nomenclature is 3.5 through 3.7. So I'm going to go out of order right now because I think going through 3.5 through 3.7 is useful for this. Organic is based on carbon, you know, organic, well first, what are organic compounds? Organic compounds are, you know, carbon, hydrogen based compounds. And the reason why they separate carbon from, because does carbon, like CO2 and SiO2, you know, silicon's much more similar to germanium, tin, and lead, maybe, than carbon. Carbon's a bit unusual. The reason why carbon's separated is because of the bonding. Carbon has no problem forming carbon-carbon links. You know, other atoms don't like to form those links, but carbon-carbon bonds are strong and stable. And not only that, there are a whole variety of links that it can form. For example, we could form 4 single bonds like this to 4 other carbons. We could form a double bond like this and then 2 single bonds. Or we could form even two double bonds, like in CO2, although CO2 is what we call an inorganic compound. There are certain carbon compounds that are considered inorganic. CO2, carbonate, a few others. But most of the others are considered organics. We can form a triple bond and a single bond. And so it's a wide variety. Plus, chains are stable. And so remember when I was talking about alcohols, I was talking about the long carbon chain. Did I say something about that? Like hexanol. Hexanol had how many carbons in the chain? 6, you know. Well, you get these longer chains, you get 6, 10, 12, 20 or more carbons in a chain. You can form a wide variety of molecules. And so there's a huge variety of molecules, and therefore they split it off into a separate branch of chemistry. Huge variety of molecules. Too much just to combine it with everything else. So there's a subset or a specialty in chemistry that's called organic chemistry. And so separate subset of chem, which we call organic chemistry. It's still the same thing. Electrical properties are the most important. We form bonds, this kind of stuff in organic chemistry. And so let's learn some carbon chain lengths. We call this the parent chain. The parent chain is the longest continuous chain of carbon atoms. Longest continuous chain of carbon atoms. You know, it could be carbon 12 or carbon 13. Actually, it's just a mix. You know, there's going to be some carbon 12 and carbon 13 randomly interspersed in there. Carbon 12 is 99% abundance. Carbon 13 is like less than 1% abundant. It's not very abundant. So mostly it's carbon 12 atoms. If we have one carbon in the chain, you know, if there's just one carbon, the parent name is meth. That is just the base name we call meth. 2 carbons we call, do you know what we call this? F. And it doesn't have to be this, you know, it could be whatever, double bonds, whatever else, etc. 3 is given prop. 4 it doesn't even have to go horizontal. You can branch it whatever way you want, zigzag. This is but. 5 you know, you just follow it, whatever the longest chain is, wherever it's going. This will be pent. 6 is hex. 7 hept. 8 is oct. 9 is nona. 10 is deca. And so first thing you look at, how many carbons are there in a continuous chain? And then you get the parent, the base name there. And then after that, we look at the what's called the functional group. Remember what I talked about? You know, properties. If we want to understand properties, what do we look for? If you want to understand properties, you look for structure and composition. Structure and composition. So functional groups are these little structures. You know, obviously we're going to have certain compositions with atoms, structure and composition. Usually people just think of structure because they can obviously see what the composition is by looking at the structure. And so we have different structures that lead to different properties. So for example, if we have a carbon that's bonded to other stuff. It's not oxygen, but a carbon like this. We call this an alcohol functional group. And so, for example, methanol is going to have one of these COH type links in here. It's alcohol. If we have a double bond on this oxygen, it looks like an alcohol, but it isn't. If we have a double bond on this oxygen to the carbon, it makes this alcohol behave a lot differently. And so this one is no longer an alcohol, it's a carboxylic acid. Well, these dangling bonds are bonded to something else, usually another carbon or a hydrogen. Could be bonded to other stuff. And so those are common functional groups. We can also have functional groups just based on the bonding itself. So for example, if we have all single bonds in this, all the carbon whatever bonds, carbon-carbon and carbon-hydrogen, carbon-hydrogen bonds are always single, but carbon-carbon all single. We call this an alkane. Now, if there's a carbon-carbon double bond present somewhere in the chain, then we call it an alkene. If there's a carbon-carbon triple bond present, then we call it an alkyne. So we have alkenes, alkenes, and alkynes, depending on how the bonding is for the carbon chain. And so let's look at some examples of naming these things. Okay, how many carbons in this one? One, so meth. And then there are no double bonds, triple bonds, anything else, so we just call it methane. And so here's the functional group part. It's an alkane. Methane doesn't exist, but we could have something like this. This one would be called F, and it's just a hydrocarbon, ethane. These ones here are for hydrocarbons primarily, but it could be for others as well. I mean, we could have these. But what we're going to see for our class, hydrocarbons, ethane. What would ethene be? Can you guess what ethene is going to have? Ethene. E-N-E. Yeah, double bond on the carbon. And then the rest is just hydrogen. So this is ethene. What would this be called here? Ethine. Ethine, there are also common names that people memorize. Ethine is also known as acetylene. Acetylene. Acetylene is some dangerous stuff. Very dangerous stuff. You know, did you see the video of the explosion in China? Take a look at that. I mean, it's just unbelievable how big that explosion was. And apparently, I guess it was calcium carbide, right? Was it calcium or some kind of carbide thing? And the problem with carbide is, if you spray water on a carbide, you know what it makes? Acetylene. The carbide and the hydrogen in the water react, and acetylene is generated. And acetylene happens to be extremely, flammable. I mean, the people use it in torches, right? Acetylene torches for welding. But you can take a look at that video. It's just horrendous. Sometimes there's a little bit of confusion. For example, what would you call this? You'd call this butene. Okay, what would you call this? I know how many, I know carbon has a total of 4. Double bond counts as 2, triple bond counts as 3. So I know how many hydrogens put in there based on that. What would you call this? Yeah, you would call this butene also. And so we have a bit of confusion here, so we have to name these two differently. This one, yeah, you're right. This one is called 1-butene. This one is called 2-butene. And the origin of the number comes from numbering the carbon chain. Number the carbon chain. And so this would be carbon 1, carbon 2, carbon 3, carbon 4. So this one has a double bond starting on carbon 1. This has a double bond starting on carbon 2. Okay. What's this called? 3-butene? 3-butene? Yeah, unfortunately, this one is not 3-butene. Because 3-butene looks an awfully like, which one? 3-butene looks awfully like 1-butene. Here, if you take 1-butene and flip it over, it looks like 3-butene. So 3-butene and 1-butene are the same thing. The same thing, we always want the lower number. And so, you know, which one is it, 3-butene or 1-butene? No, it's going to be called 1-butene because it has a lower number, and we want the lower number rather than the higher number. All right, how about this? What do you call that? Well, it has one carbon, meth, and it's an alcohol, so we call it methanol. Methane, no double bond, all is alcohol. And so it's an alkane and the all, so methanol. Or it's also called methyl alcohol. Methyl comes from CH3. CH3 we call a methyl group. There's something missing here, because carbon needs 4 things. So there's something missing, dangling. And so this is methyl attached to an alcohol, methyl alcohol. Or it's called wood alcohol. Wood, do you know where wood alcohol, why do they call it wood alcohol? Wood alcohol because some people try to ferment wood and they generate wood alcohol or methanol. Every year, you know, this doesn't really get much newspaper coverage in the US, but in the chemistry news sites, it gets coverage. You know, every year there are, you know, tens of people who go permanently blind or die from drinking wood alcohol. You know, South America, I think last year, and then Eastern Europe. You know, I think it was this year. Number of deaths. This stuff is toxic, right? Wood alcohol. It's methanol. This one is called what's this one called? This is called ethanol. I forgot to do something. But we'll start it right now. This is ethanol, and it's also called ethyl alcohol. In organic chemistry, an ethyl group is CH3, CH2 dot. This is an ethyl group, and you can bond it to something else. And then we have the alcohol, which is just the OH group. So put these together, and you get ethyl alcohol. Or it's called grain alcohol. We know a lot of these organics are quite flammable. Right? Acetylene, alcohols are very flammable, aren't they? And can be explosive under the right conditions or lead to an explosion. Well, what is combustion? What type of reaction is a combustion reaction? Combustion reactions are also known as oxidation, redox reactions. And because in the combustion you need fuel and you need a oxidizer. And so fuel would be like gasoline, and oxidizer would be like oxygen and air. And so air fuel. Do you just memorize the things that are flammable, or is there a way you can kind of tell if something's flammable or not? So I memorized acetylene. Oh yeah, that's very dangerous stuff. You know, it should be highly flammable. You just memorize all those things? Like maybe, you know, the fire, I guess they knew. I don't know. You know, in other words, you know there are different types of fire extinguishers. If you ever have a metal fire, would you use a CO2 fire extinguisher on a metal fire? Yes or no? You could use CO2 fire extinguishers on a paper fire, no problem, or wood fire, no problem, but don't use a CO2 fire extinguisher on a metal fire because you're going to cause big trouble. Like, just like you would you use water on a calcium carbide fire? No. No. Why? Oh, because you memorize those things, you look those things in a book? Look them up in a book? So what you need to do is you need to build up some chemical common sense. You know, this chemical common sense is you have to be able to analyze certain things on your own. And how do we analyze certain things or properties? How do we get some kind of clue about the redox properties of compounds? That huge explosion in China is a redox reaction. Redox reactions are very dangerous. A whole bunch of people were killed there, right? And so what gives us some kind of clue about the properties, redox properties? Well, the structure and composition do, right? And so how do we analyze the structure? Here are the structures, here's the composition, now what? You tell me the properties. And so chemistry is all electrical in nature. And so when we count oxidation states, we're looking at counting up the electrons in these structures here. And so let's do ethanol. Yeah. Ethanol, you know, there's different ways we could write the formula. This is what we call a structural formula. This is what we call the molecular formula, C2H6O. If you look at C2H6O, looking at the composition, does the composition really tell you how the structure is? No, so the molecular formula, or the structural formula, is much more useful. You know, we can see what's going on, because C2H6O has the chance of forming what are called isomers. You know what allotropes are? Allotropes are same element, different structure. Well, isomers are the same thing except for compounds. Allotropes are used for elements, the word. Isomers are used for compounds. And so if we look at C2H6O, this could also be what we call dimethyl ether. Dimethyl ether has the same exact formula as ethanol. But the properties are different because the structure is different. And so dimethyl ether is what we call an isomer of ethanol. Two totally different compounds, totally different properties, boiling point, density, etc. These are just two different things, but they have the exact same composition. The structure is, however, quite a bit different. Do you think you could burn? I know I could burn ethanol. There's no problem with that. Do you think you could burn dimethyl ether? Would it burn in the same way? Well, we're out of time, but we're gonna start looking at oxidation states. I forgot I was gonna try to save time and do oxidation states at the same time. I forgot to do that, but I'll do it next time.